We are working on section 10.2, problem 33. We are going to find the area enclosed by the x-axis and the given parametrized curve. So first, we're going to need to figure out the t interval for this section of the curve. And since we know that the area is bounded by the x-axis, we know that that's where y is 0. Okay, so that means y is 0 means t minus t squared is 0. And I get that my t values are 0 and 1. Those will be the bounds for the integral. Now we need to figure out the orientation of the curve to decide whether we're going to use the positive or negative integral formula. When t is 0, x is 1 plus e to the 0, or 2. When t is 1, x is 1 plus e, which is approximately 3.7. And so this tells you that x is becoming more positive from the interval t is 0 to t is 1, which means the curve is moving to the right on the interval t is 0 to t is 1. And that tells us that we need to use the positive integral. So the area of the bounded region, the formula is the positive integral from alpha to beta, my t values, of y of t, x prime of t dt. So the integral from t is 0 to t is 1 of t minus t squared times x prime of t, which is e to the t dt. So I can see I'm going to need to split this up into two integrals, and I'm going to need to do integration by parts twice. So when I distribute the e to the t into the parentheses, my first integral is 0 to 1 t e to the t dt, and my second integral is 0 to 1 t squared e to the t dt. Okay, on the first integral, I can get rid of the t, and I cannot get rid of the e to the t, which means I want to make u t, which makes du dt. Then that means that dv is e to the t dt, which means v would have been e to the t. On the second integral, if you can see forward enough, you can see that we're actually going to have to do integration by parts twice here to get rid of the t squared. Once to make it a t, and then to make it a 1. In the first integration by parts, I'm going to make u t squared, again because my goal is to get rid of the t squared, which means du is 2t dt. dv will be e to the t dt, and therefore v is e to the t. So let's write out our integration by parts. The integral of u dv becomes uv t e to the t minus the integral of v du, the integral of e to the t dt. And you can see that's a very nice simple integral. That's just going to become e to the t. Then I have minus, and my second integration by parts gives me t squared e to the t minus, but that's going to become a plus when I distribute this negative sign out here. And then I'm going to have the integral of v du is 2 e to the t, oops, I missed a t, 2t, there we go, e to the t dt. So while it does seem like we might need to do integration by parts all over again, this t integral of t e to the t dt, well, that's the same thing we had in the first integral. So we can just use the work that we've already done right here and plug that in instead of redoing an integration by parts. So let's see what we have. We have t e to the t minus, well, this is just e to the t. The integral of e to the t dt is e to the t. Then I have minus t squared e to the t. And then I have plus, now I have to remember this is times 2, so 2 times what I did in that first integration by parts. So 2t e to the t minus 2e to the t. Again, that's the integrated version, and I just multiplied it by 2, all evaluated from t is 0 to t is 1. Let's clean that up, and we're going to have 3t e to the t minus 3e to the t, and then minus t squared e to the t from 0 to 1. And so I'm going to plug in here, and I'm going to get, when I plug in 1, I'm going to get 3e minus 3e minus e. And when I plug in my 0, I'm going to subtract. I'll distribute the negative sign when I'm through. I'm going to get 0 minus, that's going to be 3e to the 0, which is just going to be 3 times 1, and then minus 0. And so my 3 e's are going to cancel here, and I'm going to have negative e minus negative 3, or 3 minus e as my final answer.